Hi everyone. Today we're going to be completing our notes on 7.5 solving trig equations with identities. I want to start with this warm-up, numbers 1 and 2. Here we have the 2 cosine of 3x is equal to negative root 2. In order to solve this, we're going to divide both sides by 2. And we're going to get that the cosine of 3x is equal to the negative root 2 over 2. And so we have to ask ourselves, where is the cosine equal to negative root 2 over 2? The answer here, we get 3 pi fourths, and we get 5 pi fourths. Now this is equal to 3x, the argument of the cosine, and we also have to consider all solutions, all coterminal solutions. So we're going to add full rotations around the unit circle, so plus 2 pi k, where k is an integer. Okay. Now in order to solve for x, we're going to divide both sides by 3, and so we get our answers. We get pi fourths plus 2 pi k, and we get 5 pi twelfths plus 2 pi k. And again, that's where k is an integer. Okay. Number 2, here we have 2 sine of half theta plus 1 equals 0. So to solve this, we subtract 1 from both sides and divide both sides by 2. We get sine of theta over 2 is equal to negative a half. And then we have to ask ourselves, where is 1/2 theta, or where is the sine equal to negative a half? The answer, so half of theta, is equal to 7 pi 6 and 11 pi 6. And again, that's plus 2 pi k, where k is an integer. And then to get our solution, we have to multiply both sides by 2. So we get theta is equal to, we get 7 pi thirds plus 4 pi k, and we get 11 pi thirds plus 4 pi k. And again, that's where k is an integer. All right. So that's our warm-up. Now I want to talk about solving trig equations with Pythagorean identities. Now the only difference here from what we've just seen is that we're going to include some of these new things that we've learned in Chapter 7, including the Pythagorean identities, our sum and difference formulas, and our double and half angle formulas. Okay, so I want to start with the Pythagorean identities. Let's recall what those are. The first is the one we all know and love, cosine squared x plus sine squared x is equal to 1. And then if we divide both sides by the cosine squared, we get 1 plus the tangent squared x is equal to the secant squared of x. And then if we divide that original equation by sine squared, we get cotangent squared plus 1 is equal to the cosecant squared. So we have to be familiar with all three of the forms of the Pythagorean identities, as well as any rearranged Pythagorean identities. So when we move some of those terms around. We also have to remember our sum and difference formulas. So sine, our sum and difference formula, remember those trig functions alternate and the operator stays the same. Whereas for the sum and difference formula for cosine, the trig functions stay the same, but then the operator is flipped. We have three formulas for three expressions, equivalent expressions for the double angle for cosine, and we have one for the double angle for sine. Okay. So in order to solve these equations, we have 4 strategies. The first strategy that we're going to remember is we're going to look for a common factor. In fact, any time that we're solving equations, it's often helpful to set the equation equal to 0 and then pull out a GCF if we have one. So find that common factor. That allows us to use the zero product property and start getting some of those solutions. Another thing that we're looking for is when the arguments of those functions match. Or in other words, if I have like tangent of 2x and I have secant of 2x, or if I have like cosine of half theta and sine of half theta, if we have the argument match, there's usually some ways that we can manipulate, combine things, move things around. So we're looking for those patterns. Another thing that we're looking for, this one's important, is to get our trig functions to match. Often, these equations are going to be easiest when there's a single type of trig function. So if I have an equation that has both sine and cosine, if there's a way that I can substitute in so that I have just sine in the equation or just cosine in the equation. That's often going to make the equation easier to solve. And the last, we are going to look for the rearranged identities. So we're talking about these Pythagorean identities. For example, cosine squared is equal to 1 minus the sine squared, or sine squared is equal to 1 minus the cosine squared, right? We can move around some of these terms and get equivalent expressions. While they might not look exactly like this, they might be a form of them. All right, so let's try a few examples. Let's go over to number 1. Here we have the cosine of 2x is equal to the cosine of x. So in order to solve this, I notice that we have cosine of 2x right here. Well, I know that we have a double angle formula for cosine, so let's go back and remember those. We've got 3 of them. Now, I'm going to choose one specifically. I'm going to choose this middle one right here, 2 cosine squared of theta minus 1. And the reason why I want to choose this is because I know that the other two forms include sine, right? I know that I want to get my trig functions to match, so I'm going to specifically choose the double angle formula for cosine that is in terms of cosine, or only has cosine. So that substitution that I'm going to make here is 2 times the cosine squared of x, and then minus 1, and that's equal to the cosine of x. Now we can bring all our terms over to the left-hand side, so 2 cosine squared x minus cosine x minus 1 equals 0. And this factors into 2 cosine x plus 1 and cosine x minus 1. Using the zero product property, we have 2 cosine x plus 1 equals 0, or cosine x minus 1 equals 0. And so we get the equations cosine x is equal to the negative 1/2, or cosine x is equal to 1. In order to solve these, we have to ask ourselves, where is the cosine equal to negative 1/2? The answer is 2 pi thirds, and then plus 2 pi k. We also have add 4 pi thirds, plus 2 pi k. And again, that's where k is an integer. We also have to consider, where is cosine equal to 1? Well, that's going to be at 0, 2 pi, and every multiple of 2 pi. So we could say 0 plus 2 pi k, or just 2 pi k, okay? Where k is an integer. So this is our solution here. All right, so for number 2, I notice we have 2 tangent theta plus secant squared of theta equals 4. We've got two different trig functions here. We've got tangent and secant. One of the things that I notice as well is that we have secant squared, so immediately my mind is going to one of the Pythagorean identities. Let's go ahead and make that substitution for the 1 plus tangent squared so that we have a single trig function in this, single type of trig function in this equation. So we have 2 tangent theta plus the substitution for secant squared is 1 plus the tangent squared, and that's equal to 4. So let's go ahead and write this in standard form. Move everything over to one side. So we have tangent squared plus 2 tangent theta, and then subtracting 4 from both sides, we get minus 3 equals 0. This factors to the tangent of theta plus 3 and the tangent of theta minus 1, and that's equal to 0. And then we can use the zero product property to get equations. Tangent of theta is equal to negative 3, or tangent of theta is equal to 1. Let's go ahead and solve the right-hand equation here, because we know where the tangent equals 1. It's positive 1 in quadrants 1 and 3, specifically pi fourths and 5 pi fourths. We can just call this pi fourths plus pi k. Instead of full rotations, we can say plus half rotations, where k is an integer. Now the other one, because this doesn't lead to an angle on the unit circle, one of those special angles anyway, we have to use our calculator. So to get theta, we're going to pull up our calculator and do the inverse tangent. Oops. We're going to do the inverse tangent of negative 3. I'm going to hit Control Enter to get a decimal approximation. Oh, I'm in degrees. Let's switch that to radians. Okay, so we get negative 1.249 radians. Okay, so we get theta is equal to negative 1.249 radians. Okay. Now, Our calculator is only going to give us the answer in quadrant 4, that negative angle in quadrant 4. Remember the range of the inverse tangent. Because this is an equation, we want to solve for all values theta that satisfy the equation. So we know that the tangent is equal to negative 3 as well in quadrant 2. So we have to consider the angle directly across from this in the unit circle. So what we can do is add pi, and that's going to give us that half rotation. So I'm going to add pi to the answer. So add pi. I'm going to hit Control Enter, get that decimal approximation again. We have 1.893. Okay, so theta is equal to 1.893, and that's that angle in quadrant 2 that is directly across from the negative 1.249. Okay, so what we can say is we can take that 1.893, and because we know that every other angle solution is a half rotation around, we can just add pi k to that as well, where k is an integer. All right, let's go ahead and flip the page. All right, so let's get some practice. Here we have find all solutions. 1 plus the sine x is equal to 2 cosine squared of x. So first thing I notice is that we've got cosine squared. Let's substitute that for one of our Pythagorean identities. So we have 2 times the quantity 1 minus sine squared. After distributing that 2, we get 1 plus sine x is equal to 2 minus 2 sine squared x. And then let's bring everything over to one side. So we have, moving everything to the left-hand side, 2 sine squared x plus sine x, and then minus 1 is equal to 0. And this factors into 2 sine x minus 1 and sine x plus 1 equals 0. So we get the equation sine x is equal to positive 1/2, or sine x is equal to negative 1. So we get solutions. X is equal to pi 6 plus 2 pi k. We get 5 pi 6 plus 2 pi k. And then for that second equation, we get 3 pi halves plus 2 pi k, where k is an integer. Okay. All right, so number 2, here we have 2 sine squared of theta minus cosine. Let's go ahead and make that substitution for sine theta this time. So 2, 1 minus the cosine squared of theta minus cosine theta is equal to 1. And then distributing 2 minus 2 cosine squared minus cosine is equal to 1. We'll write this in standard form and then also set everything equal to 0. Because this is a negative 2 in front of the cosine squared, I'm going to move that over to the right side, so everything's going to be on the right side. So 0 is equal to 2 cosine squared, and then plus cosine theta, and then minus 1. Okay, so we're moving everything over to the right-hand side. This looks pretty similar, actually, to the last problem. So we have 0 is equal to 2 cosine theta minus 1, and then times cosine theta plus 1. So 0 product property, we get cosine of theta is equal to 1/2, or cosine of theta is equal to negative 1. So we get solutions for theta. We get pi thirds plus 2 pi k. We get 5 pi thirds plus 2 pi k. And then we also get where cosine is negative 1. So pi plus 2 pi k. And then where k is an integer. Okay. All right. Number 3. So here we have the tangent squared of theta minus 2 secant x is equal to 2. I'm going to make that substitution for the tangent squared. So I know that the tangent squared is equal to secant squared minus 1. And then we have minus 2 secant x equals 2. Let's bring everything over to the left-hand side and put it in standard form. So we have secant squared of x minus 2 secant x, and then minus 3 equals 0. And then factoring secant x minus 3, secant x plus 1 equals 0. We get secant x is equal to 3, or secant x is equal to negative 1. Now, you could plug this into your calculator, but I want to show you a trick. Because this is the reciprocal functions, we can take the reciprocal of both sides. We have the cosine of x is equal to the reciprocal 1/3, or the cosine x is equal to the reciprocal, which of negative 1 is still negative 1. So this right-hand equation we can solve. We know that the answer is pi plus 2 pi k. Okay? But the other two we do need a calculator for. So let's go back to our calculator. We're going to take the inverse cosine of, is it positive or negative? Positive 1/3. So 1 divided by 3. I'm going to hit Control Enter to get a decimal approximation. We get 1.231. Okay, so 1.231 plus 2 pi k. Now, remember, the inverse cosine gives us answers in quadrants 1 and 2. We know that the cosine is also positive in quadrant 4, so we're going to subtract this from 2 pi to get our other angle. So I'm going to take 2 pi and then minus our last answer. So I'm going to hit Control and the negative key, and that's going to give us the last answer that we had. So we had 5.052. Okay. 5.052 plus 2 pi k. And as always, that's where k is an integer. All right, so here's our three answers. Okay, number 4. I notice that we've got a double angle for sine here. Okay, so I'm going to use our double angle formula for sine. So we have 2 sine theta cosine theta, and then times another sine theta minus cosine theta is equal to 0. So let's combine some of these things. We have 2 sine squared cosine theta, and then minus cosine theta equals 0. I notice a common factor of cosine theta, so let's factor that out. 2 sine squared minus 1 equals 0. And then 0 product property. We're saying where cosine is equal to 0, or 2 sine squared of theta minus 1 equals 0, or where sine is equal to plus or minus the square root of 2 over 2. So real quick, the way that we get that is we are adding 1 to both sides, dividing by 2, we get 1/2 equals sine squared, and then square rooting, we get plus or minus 1 over root 2, which rationalizes to root 2 over 2. Okay? So answers here, where cosine is equal to 0, well, we would have pi halves and 3 pi halves, or pi halves plus pi k. And then for the other equation, where is sine equal to plus or minus root 2 over 2, we have pi fourths plus pi halves k, where k is an integer. Okay. The reason why we have pi fourths plus pi halves k is because it's every quarter rotation around the unit circle. We could say pi fourths plus 2 pi k, 3 pi fourths plus 2 pi k, 5 pi fourths plus 2 pi k, and 7 pi fourths plus 2 pi k. Or we can consolidate and just say it's every pi fourths plus that quarter rotation. Okay, last two, here we go. We have cosecant squared plus equals cotangent of theta plus 3. So I notice we have cosecant squared. Let's use that substitution. Pythagorean identity, 1 plus the cotangent squared. And so then we get equals the cotangent of theta plus 3. Okay, let's move everything over to one side, combine like terms. Cotangent squared theta, and then minus cotangent of theta minus 2 is equal to 0. And so we get the cotangent of theta minus 2, and the cotangent of theta plus 1 is equal to 0. So we get cotangent of theta is equal to 2, or cotangent of theta is equal to negative 1. Okay, so going back to our calculator, actually we could do that right-hand equation. We know where the cotangent is equal to negative 1. That's going to be in quadrants 2 and 4, and they're directly across from one another. So 3 pi fourths plus pi k. That's our first solution. And then for the other one, we're going to do the inverse cotangent of 2. So let's go back to our trig functions. Inverse cotangent of 2 Control Enter gives us a decimal approximation, 0.464. 464 plus 2 pi k. However, we also have to consider the angle in quadrant 3. Remember, the cotangent is positive 2 in quadrants 1 and quadrant 3. So to find that other angle, we're going to add pi to get that angle directly across from it. So we're going to add pi, Control Enter, 3.605. So actually, we could just say that 0.46 and then plus pi k. And so that's just saying plus that half rotation. So that's a great way to consolidate that one, actually. Let's see that. Okay, last one. Here we have the double angle for cosine. We also have cosine squared. Okay. So let's go ahead and let's do the double angle formula. So we have 2 cosine squared x, and then minus 1 is equal to cosine squared x minus 1/2. Now, I noticed that we've got a cosine squared x term on both sides. We've got 2 on the left-hand side and 1 on the right-hand side. Let's just subtract cosine squared from both sides. So we get cosine squared of x. And you know what? Let's add that 1 over to the other side as well. So we get is equal to positive 1/2. Square rooting both sides, we get cosine of x is equal to plus or minus the square root of 2 over 2. And so we get x is equal to pi fourths plus pi halves k. It's those quarter rotations where k is an integer. All right, and we forgot to say that for the last one. K is an integer. All right. So these have been our notes on 7.5, solving trig equations with the Pythagorean identities. We're going to get a lot of practice, so we'll see you tomorrow. Goodbye, everyone.